Origami is the traditional Japanese art of folding paper. By taking a square piece of paper, it can be folded into just about anything. Although origami has been around for centuries, only recently has it become the subject of mathematical inquiry, and I have decided to delve into the world of the phenomenon known as origami. Before we get started, we need to set some ground rules. First, we will only use one sheet of paper, and second, no cuts, only straight folds. The first thing I did was unfold a paper crane. I noticed that when it was unfolded, it retained the important folds and was easy to put back. I also noticed that some folds, like the one that goes through the wings, don't contribute to the crane at all. From there, I decided to outline the important lines. By doing that, I can get a better picture of how the crane folds. It was hard to figure out which lines were important, but I soon realized that the folds that mattered were the ones that made the paper rise. What I mean by that is when you fold the paper one way, it will make a peak called a mountain fold, and when folded the other way, it's a valley fold. So I drew along the mountain folds and the valley folds. However, there were some places that were folded in both directions, and because of this they lie flat, so they don't matter. While I was drawing out the fold pattern, I started to think about it as a graph, where all the mountain folds and valley folds are edges. Also, the edges of the paper itself will be considered edges of the graph. My initial thought about the fold pattern was the colorability of the faces. In other words, I wanted to know the least amount of colors possible to color the graph such that no two faces share an edge with the same color. I started with the smallest possibility of colorability, 2. It turns out the graph of the crane is, in fact, two colorable. For the faces to be two colorable, all the vertices need to be of an even degree, excluding the outermost vertices. The only way to fold a vertex with an odd degree is to fold a previously folded edge in the opposite direction, making it neither a mountain fold or a valley fold, so it wouldn't be part of the graph anyway. Now that I found all this out with the crane, I needed to know if it would work with another origami sculpture, so I made a Lotus Blossom and repeated the same process I did with the crane. Although the pattern looks different, the Lotus Blossom, just like the crane, is two colorable. To prove to myself that I wasn't just getting lucky, I folded an arbitrary shape to see if it was also two colorable. To my satisfaction, it was also too colorable. But I wasn't ready to stop there. I wanted to know whether or not these origami patterns had Euler circuits or Hamilton cycles. So I folded another arbitrary shape to see if it would have any. I decided to look for Euler circuits first. An Euler circuit is a path on a graph that passes along every edge. The shape had no Euler circuits. This is because a graph cannot contain an Euler circuit if it has a vertex of an odd degree, and since the edges of the paper are edges of the graph, we can see several vertices with odd degrees. Since there were no Euler circuits, I decided to try my luck with Hamilton cycles. A Hamilton cycle is a path on a graph that passes through each vertex once. My arbitrary shape did, in fact, have a Hamilton cycle. My next step was to see if the crane and the Lotus Blossom also have Hamilton cycles. and both the crane and the Lotus Blossom had Hamilton cycles. There is so much more I want to learn about origami. For instance, will what I have learned hold up against more complicated pieces, or will they have an entirely new set of rules? Unfortunately, that's a question for another day.